Hi students, welcome back to this tutorial and we can consider code converters in our coming videos, and in this video we can consider a case that is binary to BCD code conversion as well as its reverse, that is BCD to binary conversion also. So we can start with this binary to BCD code conversion. So the system is conversion of binary to its equivalent BCD, right? So the inputs are binary numbers. Here we are going to consider the 4-bit representation of binary numbers. So using this 4 bits, total 2 raised to 4, 16 different binary patterns are possible. Considering here 4-bit inputs. Using 4 bits, total 2 raised to 4, that takes 16 different possibilities are there for our inputs, right? So that 16 different input patterns are represented here in this input table. And we can assign some label for each and every position of this 4 bits. B0 indicate the least significant bit, B1 the second least significant bit, B2 the next bit, and B3 finally the MSB bit. Okay, and here listed all possible 16 different combination using this 4 bit. So these form our binary number, the input system. And for the output, we need to generate this table. Here we need to get the BCD equivalent of each of these input pattern. We have already discussed about this BCD number, and we know that from this case, from the 0 to this 9, the BCD and the binary representation both are the same. From the 0 to 9. Beyond this 9, the binary and the BCD are different. So here consider this output table, truth table for this outputs. Here we are considering 5 different labels or 5 different bits. Why? Why? Because after this 9, from 0 to 9, the BCD and the binary are the same. That means using the 4 same bits, we can represent the BCD equivalents of the input from 0 to 9. That means up to this. It is clear from this table. From the 0, this 0 to this 9, the 5th bit is 0. Right? That means using the same 4 bit, we can represent the BCD equivalent of each and every binary number from 0 to 9. And consider the remaining cases, that is beyond this 9, the BCD and the binary are different. Right? So consider here, this is the 4-bit representation corresponding to our decimal 10. Right? This decimal 10, how to represent this 10 in its BCD form? In BCD, we need to represent 4-bit representation, or we need to assign the 4-bit equivalent for each and every symbol present here. This is 10. 10 contains 1 and 0. Right? So in BCD of 10, we need to write the BCD of 0. That is 0, 0, 0, 0. Again, BCD of 1, that means 0, 0, 0, 1. So this is the BCD of decimal 10. But the binary of decimal 10 is 1010. That means after 9, the BCD and binary of a decimal number is different. Okay, so from this pattern, this BCD pattern of our decimal 10, it is clear that for representing the BCD of decimal 10, we need a minimum of 5 bits. Right? That is why we are considering this 5th label D4 here. So for representing the BCD of 10, the BCD of 10 is actually 1, 0, 0, 0, 0. 1, 0, 0, 0, 0. Okay, so for representing or getting the BCD of a binary number which is greater than our 9, then we need a minimum of 5 bits. And again, consider decimal 11. For the 11, the binary equivalent is 1011. But its BCD is get the BCD of each and every symbol present in this 11. So first this one, that is 0001. And for this next one, this is 0001. This is actually the BCD of decimal 11. So from this representation, it is clear that for representing the BCD of 11, we need a minimum of 5 bits and the BCD is 10001. So this is 10001. So for representing the BCD of number which is greater than 9, we need a minimum of 5 bits. That is why we are considering the fifth position here in this output table, because we need to consider or we need to derive the BCD of total 16 different symbols. In this we have numbers from 0 to 9, and after that we need to represent BCD of 10, 11, 12, 13, 14, 15. Right. So for representing the BCD of numbers that is from 10 to 15, we need minimum of 5 bits. So in our output, we need to consider 5 different bits. And from 0 to 9, the fifth bit is 0. And after 9, for the remaining numbers, that is from 10, 11 up to 15, the fifth bit is 1. Clear? So this is our BCD. And this is our input binary, and this is our output table which contains the BCD equivalent of each and every binary number listed here. Now our next task is we need to get the simplified expression corresponding to this D4, D3, D2, D1 and D0. We need to get the simplified expression, right? For that we need the CAMAP simplification for each and every this bits D4, D3, D2, D1, D0. So first just derive the SOAP form corresponding to D4, D3, D2, D1, D0. This will help you to derive or simplify the CAMAP, or we can see, directly write the CAMAP by using this SOAP form. So while analyzing this output table, SOAP form corresponding to this D4 is first consider this column for this D4, and wherever this 1 present here, here in this case, this and up to this. Okay, so this is actually 9, 10, 11, 12, 13. Okay, this is actually 10, 11, 12, 13, 14 and 15. So in case of D4, this particular column contains ones only for these much inputs. That is for 10, here D4 is 1, and for 1, and for 11, here it is 1, 12, 13, 14, 15 also, here it is 1. So in our SOAP form, for D4, min terms and the product terms are 10, 11, 12, 13, 14 and 15. And for D3, similarly for D3, these two cases contains 1. This means this is the BCD corresponding to 8 and this is the BCD corresponding to 9. So here it is. D3 means SOAP form. It contains min terms 8 and 9. And D2, consider this table, this particular column. D2, here it is 1, here it is 1, and these two cells contains 1 again here also. Okay, and this is actually min term 4, this is min term 5, This is midterm 6, 7. 4, 5, 6, 7 and again 14 and 15. So midterm or the SOAP form corresponding to D2 is 4, 5, 6, 7. This is actually 4. Okay, 4, 5, 6, 7, 14 and 15. Next is D1 and here it is 1, here 1, this 2, 1, again this 2 location. So this is actually corresponding to input 2. This is 3. So D1, the SOAP form is 2, 3, 6, 7, 12, 13. 2, 3, 6, 7, 12, 13. Here it is. And for this B0, the ones comes in cells like 1, 3, 5, 7, 9, 11, 13 and 50. Okay, 1, 3, 5, 7, 9, 11, 13, 15. Now using this expression, now we can directly draw the K-map while referring this SOAP form. Okay, so these are the K-map corresponding to D4, D3, D2, D1, D0 and here in this expression, in this first case, in the first K-map, the expression corresponding to D4 is here. For this blue group, the expression is here the common term is this one, B3 and B2. Or and for this red group, the common terms are B2 and B3 and B1. B3 and B1. So the simplified expression for D4 is B3, B2, B3 and B2 or B3 and B1. Similarly for this D3, this is the only one possible group here and the common terms are this and column wise B1. B1 with value 0. So the simplified expression D3 is B3, B2 complement, B1 complement. B3 and B2 complement and B1 complement. B2 complement means B2 with value 0 is common, B1 with value 0 is common. And B3 in its original form here it is B3 with value 1. Okay. So, and for this D2, the blue group expression is this blue group. The blue group expression is B3 with value 0, B3 complement. B2 with value 1, B2. Means B3 complement and B2, this one. And next for this red group, B2 is common and B2 with value 1. So B2 exists in its original form and column wise B1 is common. So B2, B1. Okay, and again for this D1 simplification using this K-map, for this blue group B3, B2 and column wise B2 is common with value 0. So B3, B2, B1 is common with value 0. In column wise B1 is common with value 0. So B3, B2, B1 complement. This one. And for this red group, B3 is common with value 0, B1 is common with value 1. So B3 complement B1. This two. Again for this D0, here for this 8-celled group, B0 is common. Only one term B0 is common with value 1. So B0. D0 is B0. Okay. Now using these expressions, after the simplification using this expression D4, D3, D2, D1 and D0, we can draw the circuit like this. So for more clear diagram, we can follow this particular format or this particular pattern of circuit. Simply write the input like this B3 and note the B3 complement. This is actually B3 complement. Next B2. Draw a vertical line from this B2. Next mark this B2 complement. That means B2 taken as an input to a NOT gate, then this become B2 complement. Again, this is B1 and this is B1 complement. This is B0, and if we need B1 B0 complement somewhere, we need to pass this B0 through a NOT gate, then this will form B0 complement. Actually, in this in our previous expressions, it is clear that in this expression we don't want this B0 complement anywhere. Okay, so we don't want to draw this particular portion here. So we can derive first D0 means, from this expression it is clear, D0 means B0 itself. So directly draw a line from this B0, this will form D0. Next, for this G1, the expression is B3 and B2 and B1 complement, or B3 and B1. B3 complement and B1. Right. So this is a product term. Take these three input to an AND gate and its output is OR with another term, another product term, that is B3 complement and B1. Okay, so pass B3, B2, B1 complement as an input to one AND gate, this one. Next, B3 complement and B1 as taken as an input to this AND gate, and these product terms are taken as an input to one OR gate, and the output of this OR gate form the expression for or the circuit corresponding to D1. And similarly for our D2, this is B3 complement and B2 plus B2 B1. So take B3 complement and B2 as an input to this AND gate. Again, B2 and B1 taken as an input to this AND gate. Its outputs are taken as an input to one OR gate, and the output of this OR gate form. Okay, similarly we can finish this D3, D4, etc. So this is the circuit corresponding to our code conversion binary to BCD. Similarly, we can consider next the reverse conversion, that is input is BCD and we need to derive the binary equivalent of each and every BCD number which is given as an input. So here it is the table. And here consider 4-bit representation. For the easiness of our simplification, take input with 4-bit representation and list all possible input combinations here. So using 4-bit, we can take 2 raised to 4, total 16 different input combination over here in this input table. Okay, so actually this input is BCD number, right? So from this, it is clear that from 0 to 9, from the 0 to 9, we can directly write its binary equivalent in our output table. So the binary equivalent of each and every number takes minimum 4 bits. So in our output table, we have this 4 different position labels like B0, B1, B2 and B3. And for this BCD 0000, corresponding binary is 0000 itself. And for 10001, corresponding binary is 0001 itself. And for 2, here the BCD is 0010 and corresponding binary is 0010. And up to 9, both the BCD and binary are the same. And beyond that, here the BCD pattern is given like 1010 here in this input table. But is it a valid BCD? No, this is not a valid BCD, this 1010 pattern. So for this particular given BCD pattern, we can't derive an equivalent binary. Okay, so we can represent here don't case. We can mark or we can put don't case here, because this representation here in this input, the representation is like 1010. This is not a valid BCD form of any of the decimal number, right? So in this case, we can mark don't cares in our output. Similarly, for this 11, this is not a valid BCD of any of the decimal number. So we can directly assign don't care for this particular input in our output table. Corresponding to this input, the output table contains full of don't cares. And similarly for this also, this is not a case of valid BCD for any of the decimal number 1100. This is not a valid BCD. So write full of don't cares in our output table, and the same repeat for this 13, 14 and 15 also. Okay, so this is our output table, and while analyzing this output table, we can derive separate expression corresponding to B3, B2, B1 and B0 next. So for this B3, after assigning these values over the CAM app, after simplification, we get a simplified form. Here B3. We need to derive expression for this output B3, and the expression is based on our input labels. We need to derive expression for B3 and the expression is based on our input values. Means output in terms of input. So B3 is actually from this simplification, or this group actually indicate D3 is common here with value 1. So B3 is equal to D3. And for this case, second, the expression for this B2, put all these values properly here in this CAM app, and we can derive a group like this. And this group actually indicate D2 with value 1. So B2 is D2 itself. Next is here, and the expression is for B1, and here in B1, all these values properly in the scam app, and while simplifying this, we get this B1 as here D1 is common for these much cells. D1 is common with value 1, so B1 is D1. Again for B0, this particular group formed here, and here D0 is common with value 1, so B0 is D0. Okay, so here it is clear that B3 is directly formed D3, B2 is from D2, B1 from D1, B0 from B0. So this is circuit corresponding to our BCD to binary converter, binary code converter. B3 means D3, B2 means D2, B1 is D1, B0 is D0, which is actually derived from our CAM app. So we can directly mark this. D3 is B3, so D3 is directly connected to B3, D2 is connected to B2, D1 is connected to B1, D0 is connected to B0. So all these are about the conversion of binary to BCD and BCD to binary. The procedures are all the same, but we need to concentrate over that truth table. We need to consider which is the input and which is the output. So if it is possible to derive output table corresponding to the input table, then from that output table we can simply generate the expression after that expression derivation. Using that expression, we can directly draw that circuit. So this is the procedure for our code conversion. So we can stop here this video, and in our next video we can consider some more such type of conversions. Okay, thank you.